Subhajit. So, am I audible? Okay, so as you mentioned, I'm a PhD student at ISI Kolkata, working with this guy, Soumendra Sundar Mukherjee. And so today I'll be talking about something of different flavor, which is not probably that geometric. So this talk is about a particular random matrix model, but I'll give you one connection with p-spin models in my talk. So I'll assume that you guys know nothing about random matrices, which is obviously false. So even if you don't know, I'll just define everything and keep everyone with me. So as I said, it's a talk on random matrices. So what's a random matrix? It's a matrix whose entries are random variables, independent or dependent, whatever. So that will be specified. In random matrix theory, so suppose A is a random matrix, A11, A12, etc. A21, A22. And this is say n times n, the dimension. So throughout this talk, we'll restrict ourselves to symmetric matrices. The reason is that the eigenvalues are real in case of symmetric matrices. And moreover, they are easier to analyze. So there is so-called this trace moment formula, which says that the say the sum of the kth power of the eigenvalues is given by trace of the kth power of the matrix. So, and there are a few other relations that we can exploit for symmetric matrices. So they are easier to analyze. We'll be sticking to them. So for us, these two entries will be equal and so on. And so what kind of questions are we interested in? We're mainly interested in the spectrum of this matrix. That means it has n many eigenvalues, lambda1 up to lambda n. So some questions about the spectrum as the dimension becomes large. So what kind of questions? So first of all, as I said, these will be the eigenvalues, real. So, okay, so number 2 would be, what about the behavior of this lambda1 or lambda n or maybe lambda 2? So these kind of questions are called like edge questions, questions about the edge of the spectrum. So questions about lambda 1, lambda n, maybe lambda 2, etc. Or maybe jointly. And why number 1 is hollow? Because this is like the most natural thing that comes to your mind. But it turns out that this is probably the second easiest thing to analyze. The easiest one is what is called say empirical spectral distribution. So this talks about all the eigenvalues, how are they behaving together. So this definition is very simple. So if you have some matrix A, random or not, you can define this empirical spectral distribution to it, or ESD. It's just defined as this probability measure 1 over n, sum over I equals 1 to n. So basically, on each of the eigenvalue, you put uniform mass. So what is so if A is a random matrix, what is the behavior of, so this is a random measure in that case, why is it converging weakly? So that's like the first question. And this kind of questions are called, this kind of results are called bulk results. These are called edge results. And thirdly, we have something more. This is called directional spectral measure. So one thing you can notice here is that this measure only depends on the eigenvalues, not the eigenvectors. However, this is another bulk related measure which will incorporate both the informations about both the eigenvalues and eigenvectors. I'll be defining them there shortly. And there are other questions about things like singularity, probability. What's the probability that such a random matrix is singular, etc. But I'll not be talking about that. Those are a bit different. Okay, so and these off diagonal entries, so these guys, they should be normal 0, 1, and the diagonal entries should be normal 0, 2. A little caveat, people usually call 1 over square root ng to be the GOE, but I'll be using this convention. This is GOE for us, okay? And we know pretty much everything about this matrix. All right, so my goal is to first define a tensor version of GOE, but then again, I don't know how to handle the eigenvalues of tensors because they are not even very well defined. So from that tensor, I'll then again construct a matrix through contractions, and that will be a random matrix, and we'll be talking about the spectrum of that random matrix. That's pretty much the goal. Okay, so before that, we can also define this joint density of all the entries via this function. So modulo the fact that the matrix has to be symmetric. So you assume symmetry of G, and then you say that the joint density of all the entries is given by proportional to this function. That will be an equivalent definition of GOE. And as I said, we'll be looking at a tensor version of GOE. All right, so what is a tensor? A matrix is a collection of n square many random variables. They are indexed by 2 numbers. So a tensor of order R is a collection of n to the power r many random variables indexed by r many numbers, I1 up to IR. And it's random if all the entries are random variables. Now a tensor is called symmetric if you take any permutation of this index set, the entry does not change, just like matrices. And then I say that the modulo this symmetry, I want symmetry, and I say that the joint density of all the entries of the matrix should be given by this function. So it's the Frobenius norm of the tensor, defined as like matrices, square root of square sum of all the entries. And there is a scaling of 1 over 2r. If r is 2, you get back GOE, of course. And now the equivalent definition of GOE is this, that you need all the random, all these n to the power r many variables to be independent modulo the symmetry, and the distribution of individual entries should be centered Gaussian with this variance, r over number of permutations of this tuple, tuple I. So here I is a vector, I1 up to IR, this index. Okay, so for example, if R is 4, the variance of this entry will be given by 4, which is R, divided by the denominator is number of permutation of 1, 2, 2, 3, which is 4 factorial by 1 factorial, 2 factorial, 1 factorial, which gives you 1/3. So that's how this tensor is defined. Okay. So as I said, I won't be working with the tensor. I'll form a matrix out of it again. So that we achieve through this contraction operation. So I have this R tensor, script G, which is called the GOT, I defined. And suppose I have this R minus too many unit vectors. And here is how I define a contraction of this G in this R minus too many directions. It's very simple. So the ijth entry of, so first this M will be an n by n matrix, and the ijth entry of this matrix M will be given by this linear combination of this G, the entries of G. So let's understand it better. So Mij, so you fix the first two indices of G to be I and J, and then this R minus too many indices are all free. And you multiply that with these coordinates from the unit vectors that you are given. These are all the deterministic unit vectors, and then you sum it over. So it's a sum of n to the power R minus too many Gaussians, basically. And so the whole thing is also a Gaussian, it's a Gaussian variable. And so the matrix that you will get out of it will be, again, symmetric, because your G was symmetric to begin with. And all the entries will have Gaussian distribution. However, the entries will be highly correlated. And that's the challenging part of this model. Because the more independence you have on a matrix, it's the easier it is to analyze. And it has many dependence, because if you think about it, each entry is linear combination of a bunch of independent things. But these independent variables can be common between two entries. So from there, you will get a lot of dependence. And yeah, you have long range dependence. And so, for example, if R is 4, you can, this is just what this one boils down to. Okay. However, too many indices. So I will just drop them. So what I'll do, I'll consider the case where all these are equal. So that case is called pure contraction. And I'll denote all these ULs by this W. So in this work, I'll be mostly focused on the pure contraction case. However, at the end, if I have time, I'll show you one result about mixed contraction, but only for the case when R is 4. But let's first focus on pure contraction. Okay, so here is a bit of a motivation behind looking at this problem. So here you can see a little bit of spin glass. So if you take this Hamiltonian, where this script G is as I defined, then this model is like a brother of this classical spherical R-spin glasses, a little bit different because my variance structure, I believe, is a bit different. And the Hessian of corresponding to this Hamiltonian is actually given by this square root times M, this matrix, the M which we are considering. So this is one of the motivations behind looking at this matrix, the spectrum of this matrix. And secondly, it has this connection with hypergraphs. So let me quickly tell you what are hypergraphs. So a graph is, you have a vertex set. Let's call the vertex set to be this n, the integers of 1 up to n. And suppose you have H set E. So this is classical graph where E is a subset of this. Of course, if it's undirected, you'll have some relation here, but forget about that. But let's consider now, so what are hypergraphs? You will have a vertex set, and you will have again, let's say this H set E, but this E will be a subset of n to the power R. So if that is the case, then this kind of this is a hypergraph. Not only that, this kind of hypergraphs are called R uniform hypergraphs, because at any hyperedge consists of R many vertices. Okay, so if you think about it, so corresponding to a graph, you get adjacency matrix. Corresponding to hypergraph, you will get adjacency tensor. So this tensor will have n to the power R many entries, which is, if R is large, which is pretty large. However, from this tensor, let's call this tensor to be script A, the adjacency tensor. From this, if you contract this tensor, say, in this direction, so this is the all one vector. Okay. In this direction, I should take this contraction, R minus 2. This guy will be a matrix, just like before. This, what we called hypergraph adjacency matrix. This is hypergraph adjacency tensor. Now, the thing is, what is the ijth entry of this matrix? This is basically number of hyper edges containing the vertices I and j. So number of hyper edges containing vertices I and j. So basically, this matrix also captures a lot of information from the adjacency tensor. For example, many connectivity problems you can solve by looking at this matrix instead of the tensor. And but this has only n square many entries. So you can decrease your complexity, computation complexity, by a great margin if you use this matrix A instead of the tensor script A. Right, so that's, but this is a bit different because we have to take something like Bernoulli for each hyper edge, Bernoulli variables to make it A dot Renyi. But we actually have a work on this where we actually replaced all these Bernoullis by Gaussians with appropriate parameters, and then we showed universality. So this Gaussianity assumption that we are having here is probably not that far-fetched. This is related to this model. So that's about the motivation. And here are a few works in the direction of this GOTE. So basically in this paper, he showed that, he defined a concept of Stieltjes transform for tensors, which boils down to our usual Stieltjes transform for matrices when the R is 2 and convergence was showed. And these three papers, these three papers considered exactly what I am considering, maybe a little different, but they considered contractions and showed that for fixed R, they evaluated, they found out the LSD. And in this one, it was mixed contraction, but yeah, so we'll be only considering pure contraction. So that's some related works. Now, let's move on. So again, before I go to the results, this is the model. For us, all these U's will be W, and in my matrix, the ijth entry will be the linear combination of these entries from script G in this way. Okay, and these are the questions that we'll try to address. So what is the LSD? I'll be defining LSD. It's related to this one, the limit of this empirical spectral distribution, basically. What is the LSD for general R? Because that is not explored. Only fixed R case was explored so far. And what is the behavior at the edge? This is not at all explored before, the edge behavior. And also, we'll try to also address this third point, directional spectral measure. And if time permits, we'll look at the mixed contraction case when R is 4. Okay, so let's get into the results now. Okay. Okay. So again, so this is the definition of empirical spectral distribution. You are putting equal mass on each of the eigenvalues. And so this is a random measure if A is random. So an expected version of this random measure is given by is defined by this. Is given by this mu bar of A, which we call this expected empirical spectral distribution, or EESD. So this is defined in the typical fashion through test functions. And the limiting spectral distribution is weak limit of this mu A or mu bar A. And here is our first result. So the EESD of this scaled version of M converges to the standard semicircle law, where this is the semicircle density. And of course, when R is 2, you get the GOE. In that case, this is well known. Probably 50 years ago, this was proved. You are putting R things. No, R can be anything. That's why the R appears here in this side. You can take R to be even bigger than N, like very, very bigger than N. Everything is allowed. And moreover, if R is very, very less than n square, you have this convergence of ESD, which is a random measure in probability. And if R is very, very less than n square, then you have almost sure convergence of the ESD. All right, so that's about the LSD, and this is a simulation where I take n to be 500, R to be 4, W to be this all one vector, appropriately normalized, and I plot the histogram, I mean the eigenvalues, histogram of the eigenvalues, and this is the standard semicircular density. It perfectly fits it, so we are good. However, you can see that there is something outside there, something outside here. And that will be the motivation for the next part of the talk, where we talk about the edge of the spectrum. So clearly, when R is 4, the largest eigenvalue is not the right endpoint of the LSD. So let's talk about that. Yeah, so this is again the LSD result. All right, so let's talk about the edge now. So lambda 1 is the largest eigenvalue of this scaled version of M. Lambda n is the largest, smallest eigenvalue of this same thing. So if R is bigger than or equal to 3, so here I'll have few regimes. If R is bigger than or equal to 3 and fixed, then this is the first order behavior of the largest and the smallest eigenvalues. So it is some function of R. Alpha is some function of R, which is explicit. Okay, so here are a few remarks. As I said, so the endpoints of the LSD of this matrix, not the previous matrix, not with the previous scaling, with the scaling 1 over square root n. So the endpoints are given by 2 by square root r minus 1 in general. So if R is 3, then this lambda 1 and lambda n, their limits stick to the endpoints of the LSD. However, if R is bigger than or equal to 4, these two eigenvalues are separated from the bulk. Okay, and this happens due to this Baik-Benarau-Specie kind of phase transition or BBP phase transition. So let me quickly say what that is. So remember, this was our scaled GOE. Suppose I add to it something like some theta x transpose. X is some unit vector, and theta is something bigger than 0, say, real number. And these two are deterministic. So let's call this matrix A. Then lambda 1 of A, this converges to 2 if theta is less than or equal to 1, 0. And it converges to theta plus 1 over theta if theta is bigger than 1. So this is known as the BBP phase transition for spiked Wigner models or spiked GOE, and that's the reason why I get this kind of phase transition at R equals 4. All right, so this is the result for R fixed. Now let's talk about the other regimes. So if R is between 1 and n, if you take just the limit here as R goes to infinity, you will get this, which turns out to be true. And in the other two regimes, so this regime is where R and n are proportional and their ratio is converging to some C, positive C, then you have a distributional limit. And this is explicit. So this xi is some quadratic function of a standard Gaussian, and lambda n converges to -1 over xi. And when R over n is going to infinity, again, I have this distributional limit. The largest one goes to the positive part of some Gaussian, and the smallest one goes to the negative of the negative part of the same Gaussian. So that's it. Okay, but now the question is, what is the fluctuation up to this regime? Because here you have distributional limit. What can we talk about the fluctuation. And indeed we can, and that's my next slide. Okay, and by the way, these all matches with the GOE. Okay, no, not GOE, because here R is bigger than or equal to 3 you need. So yeah, no, that's not true. But for GOE, I just mentioned that there is similar results, and I think the limit is, with this scaling, the limit would be 2 of lambda 1, and lambda n would be minus. Okay. So here again, I'll have 3 regimes. R is 3, R bigger than or equal to 4 fixed, and R is going to infinity, but slower than, in a slower rate than n. So the first regime, when R is 3, if you center and properly, and then your scaling would be n to the power 2/3, it converges in distribution to this thing, this minus lambda 0 and lambda 0, where this lambda 0 is the largest eigenvalue of a stochastic area operator of this kind with some initial condition. And so this is like a Tracy-Widom kind of behavior. I'll come back to that. Let's first look at the next result. Okay, if R is bigger than or equal to 4 and fixed, then the fluctuation is Gaussian and the scaling is square root n. And we have explicitly given the covariance matrix. Now here is the point. So many of you know that if R is 2, that is, if you have GOE, then the result is n to the power 2/3 lambda 1 minus 2, just for lambda 1 I'm writing this, converges in distribution to this Tracy-Widom 1, because this is a well-known distribution. And so for R equals 2, you get Tracy-Widom. For R equals 3, you get something like Tracy-Widom, and for R bigger than or equal to 4, you get Gaussian. So basically, there is this scale. So if you look at this stochastic area operator, depending on the initial condition, you will get this Tracy-Widom and this distribution and Gaussian. So depending on the initial condition, you get these 3 cases basically. So that's how they are kind of related. There is a scale where this Tracy-Widom and Gaussian are connected by something what is in the middle. And then this is a customary histogram. So this is N500, same values, and this is the fluctuation of the largest eigenvalue, which pretty well matches the Gaussian. I did not dare to draw the middle one, R equals 3, too complicated. And okay, so then and the last regime, which is again the limit of this guy as R goes to infinity, you'll get this. Oh, nothing surprising. Okay, so now let's move on to our last promised bulk result. So this is not a very popular bulk measure. So as I said, that here in the empirical spectral distribution, the eigenvectors are missing. And so that we incorporate here. So basically there, each lambda I had a mass of 1/n, uniform mass. However, here the mass would be, so first you fix some unit vector x, which is deterministic, and then the mass of lambda I would be the projection of this x in the direction ui, square of that will be the mass in the direction lambda I. And this is read as the directional spectral measure of A in the direction x. So for different x, you get different measure. And okay, so for GOE, the LSD is actually given by, again, standard semicircle. So whatever was the LSD, like the LSD for, I mean, the limit of this empirical spectral distribution is also the limit of this directional spectral measure in the case of GOE. However, in our case, we see something very interesting. So here is the setup. X is some fixed unit vector, and assume that the overlap between x and w is converging to some rho. So then for R bigger than or equal to 3 fixed, if I look at the limit of this, so here the scaling is just 1/√n. the limit of this directional spectral measure is given by this mixture. So let's understand them. Oh, W was the, yeah. So we started with this GOTE, and I was contracting with this W. So W is that fixed vector from the beginning. And so there are two atoms at the smallest and the largest eigenvalues. I mean, the limit of the smallest and the largest eigenvalues. And there is, of course, the semicircle law part. All fine. So remember that this was actually the LSD, this new SC with 1 over R minus 2, R minus 1. However, there is something very interesting appearing here, which is this mu R. This is the density of mu R. Now, during a talk, my friend Deepranjan, he pointed out that this density is actually the density of this Kesten-Mackey law. And this has a great ties to random graph. So what is the tie? So you consider the set of, so what is a d-regular graph? D-regular means each vertex have degree exactly d. So you consider this uniform distribution on the set of all d-regular random graphs on n vertices. And you write down the corresponding adjacency matrix. This matrix, if you center it properly, will gives the LSD, this Kesten-Mackey law. Okay. So these will be the exact parameter in terms of that degree d that I mentioned in our case. Okay? And this is the exact density. So this is a mixture of these three parts. And here are a few remarks. If your x and w are say orthogonal, then what happens? Then this rho becomes 0. So these two terms are not there. So you are just left with this semicircle part, and this matches with the usual LSD, the LSD corresponding to the empirical spectral distribution. And similarly, if x and w are equal, or maybe x is minus w, then the limit does not have any semicircle part. It's just atoms and Kesten-Mackey. And thirdly, if R is say 3, in that case, the largest and the smallest eigenvalues stick to the side of the LSD. So that's why there are no atoms. And that's pretty much about the pure contractions. So the proof strategy is very simple. So that's why I'd like to mention 1 or 2 lines from there. So as I said at the beginning, that the entries are highly correlated. So for looking at such a model, we first computed all the covariances between all the entries of M. There are no way close to 0 or anything. But we computed and we tried to find, is there any pattern in them? And indeed, it turns out that we can find a pattern in these covariances. And here is the main step of the proof. I show that my matrix M is in distribution equal to this guy. So let's understand this. So G is just the GOE matrix, which we know, about which we know everything, more or less. And W was from this deterministic vector that I'm carrying from the beginning, the contraction direction. So that part is deterministic. And so now this U is some normal 0, 1, and this bold V is n-dimensional normal identity. And G is, as I said, GOE. And more importantly, U, V, and G, they are all independent. So now my problem is pretty easy. So this is so here is the rank of this part is 2 basically, because it's made out of W and V only. So I have a rank 2 perturbation of the GOE, and about which we know a lot of things. We know a lot of techniques. So we use now this representation to go forward with our proof. Okay, so any question? Yeah.
The analysis is important that, right, for you, that these 3 components are independent.
I mean, life is even more easier because you can condition on this this part.
Yeah. So I'm just saying that I guess there actually you use the Gaussianity to get this decomposition to independent components. The Gaussianity is important.
Because Gaussianity, for Gaussians, if you know the covariances, you know the whole distribution.
Exactly.
So either
so my question
match
then, like let's say if I replace the Gaussian distribution with other.
Yeah. So you mean universality. So we can also do that. So so first of all, you start with any distribution, whatever you have, then you solve this problem, the problem for Gaussian. And there are some results, some universality results that takes you from Gaussianity to that whatever suitable distribution you have. So that's also there's also a result of that kind, but I did not include that here. So under certain condition on this W, so I think the W should be delocalized, sufficiently delocalized. In that case, universality holds. Okay. Now the proof is very easy. So LSD is pretty much free because there is a result that finite rank perturbation does not change LSD. So you have a rank 2 perturbation, it will not change LSD. So whatever is the LSD of this part will be the LSD of your whole matrix M, which is like scaled semicircle. For G, it is a semicircle, so you will get some scaled semicircle. That's cool. And the other two things, so this one for the edge, we can use result from this paper to conclude the edge results, fluctuation, etc. And for the last result about directional spectral distribution, we need something more advanced, but these techniques are also developed. So you basically need local laws for this kind of random, local laws for spiked GOE. That's what you need. And these are actually developed earlier. So that's how the proof goes. And I have some time, so let's talk about the mixed contraction case when R is 4. By the way, we could not do anything more than 4. I mean, we have to do some computations, but as of now, I don't know the results for general R. So let's focus on only R equals 4, because this is also great in the sense because mixed contractions were studied, but only for LSD, so not edge results. So we can give at least one edge result. So edge result when R is 4. So there is also something new here too. So here again, so let me remind you the notation: fix two unit vectors U and V. Suppose their inner product is going to some rho, and M tilde is this contracted matrix contracted by U and V. Earlier it was only W, tensor W, now U and V. And lambda 1 tilde and lambda n tilde are defined similarly for M tilde. And here is our simple result. So this, I could actually write M tilde here anyway. So the LSD of this matrix scaled by 1 over square root n converges to again semicircle, but now you have a non-trivial variance which depends on this rho. In particular, if rho is 1, you are back to the pure contraction case, and you get this variance to be 1/3, which matches with our previous result. And secondly, these are the edge results. This also holds jointly, I mean, of course. So lambda 1 tilde converges to this quantity. Again, it depends on rho. And again, if you put rho equals 1, you get back to previous result. One thing is nice is that none of them depend on the sign of rho, whether rho is positive or negative. I mean, that makes sense because Gaussian is symmetric. Yeah. Okay, so now again, the proof strategy is similar. I'll break this M tilde into a finite rank perturbation of GOE, which I exactly do here. But here, this perturbation has rank 4 instead of 2. So this is the GOE part, some constant times GOE, and this is rank 4 perturbation, rank 4 matrix, this one. Where the random part is this U, which is normal 0, 1, and this bold capital V1 and V2, which are normal 0 identity. However, they have a covariance now. And the covariance, there should be I here, there should be I. UV times, yes, I. So I missed I there, identity. So this is the covariance, and G is the GOE. So this is a rank 4 perturbation of the GOE. But here is another interesting thing. Ideally, you would expect, so here I told you this result. This is a rank 1 perturbation. Now, for rank 1 perturbation, if this is positive, you should get one outlier eigenvalue. But if I had, say, another theta prime, say x prime transpose, I should get two outlier eigenvalues, and theta prime is also, say, 0. Okay, in this regime, I mean. So if theta and theta prime are both bigger than 1, I should get two outlier eigenvalues, two values outside the spectrum in the right side. But in this case, I have rank 4, and if I compute the eigenvalues of this part, two of them will be positive, two of them will be negative. However, those two positive eigenvalues are actually very close to each other. In limit, they are same. So that's why you'll get only like two outliers. So like this. So this is, say, the bulk. This is the LSD. So lambda 1 and lambda 2 both will come here, both will fall there, and lambda n and lambda n minus 1 both will be here. So it's not like that lambda 1 is here and lambda 2 is here, not that. So that will be the picture. And here are a few open directions. So as you said, universality. I'm not very convinced about the result that we have because it requires strong condition on W. Maybe we can do better. So that's one direction. And what about the limiting direction of spectral measure for general R? Because for me, R was fixed. I believe we can handle this, but I'm lazy, so that's why it's not yet done. And the mixed contraction for general R. These are the future goals. And yeah, that's these are some of the references. This is our version on archive, which contains this stuff. These four are the references on this GOT model, some other works. And these two are two papers used in the proof of the edge. And that's all I had to say. But before I finish, I'd like to thank Subhajit, Trishen, and Piet for inviting me to give a talk. So this is my third time at ICTS, and but this is the first time I'm giving an invited talk, and also got my own personal room. Thank you. And yeah, if you have any questions, please go ahead.
In the in the convergence of the largest and smallest eigenvalues to the stochastic A operator.
Yeah.
So can you show that result?
Yes. Yeah.
Yeah, that one. Is it the negative of the same, or is it two independent ones actually? So the
no, I as far as I know, one will be the negative of the other.
Usually the largest and smallest are uncorrelated, right? Is something special going on here? Unless I misunderstood, lambda 1 and lambda n are smallest and largest, right?
Yes, yes.
They should become independent of each other, right?
Is it? We used a result from another paper here. And, this is what we got.
Okay.
I'm not, so I'll talk to you.
Okay, so let's thank Himasish again, and then we resume at 2:15.